Hello and welcome back to the lab. Today on the bench we have a blank slate. In a few videos back, I did a couple VTVMs for a makerspace down in Greenville, Tennessee, and the way I had to return those meters kind of bothered me a little bit because when projects leave the lab, I want them to be done 100%, nothing to worry about. Given the situation that we had going down there, and not 100% knowing where the equipment was going to get set back up, I knew they were going to sit on the shelf for a while. So that's why I did not put a battery back in for the ohms range. If you have a battery in one of those meters and you're going to store the meter for a while, this is for not even VTVMs, but a Simpson 260s triplet, not triplet, 630s, a couple of others. You should really take the batteries out of the meter because over time the batteries can pop, leak, corrosive gases, and do quite a bit of damage. The batteries in those meters were some of the reason we had to replace so many parts, especially that 20 megohm resistor and a couple of other things. A quick Google search will show up battery eliminators. Now these are essentially modern circuits that go in the meters that'll output an adjustable voltage into the battery circuit, and they hook somewhere into power in the meters. I've been discussing with a couple of other techs pros and cons, various of kicking around the alternatives for using a battery for the ohms range. I know some meters, the power transformer's got enough overhead you can tap off of a couple windings and get enough current and go through some regulation and use a circuit. There are other meters on the market where the power transformer is right at its limit and there is no overhead. Don't even try it. It overloads the power transformer and bad things happen. I was noodling around on some parts websites, and I was curious as to what was the smallest, physically sized, smallest power transformer I could find, and could I find something, modern or otherwise, that would give me a decent voltage, but my target design physical limitations was, can I make this thing about the size of a D battery? And lo and behold, Hammond has this guy. So this is a 110 volts mains power transformer, center tapped. Here's our center tap, but end to end it's 2.5 volts at 1 amp. This will give me an amp of 2.5 volts out of 110. So what I'm thinking, at least right now, is wiring this across the power switch, because the power switch will have the overhead, but we're adding a transformer and not relying on the power transformer in the meter. So if we take a look, here's the ratings. Come on, focus, camera. 115 volts, 60 hertz. 2.5 volt center tapped at 1 amp, so it's a 2.5 VA transformer. Tiny thing, too. Let's see if I can get some scale. Here is a modern, what is this? A 2.2 microfarad at 400 volt capacitor. And some other scale. Oh, a lot of people will be familiar with this. 9/16 inch box end wrench. So very tiny power transformer. Now, if you search Amazon and a couple of other places, you'll find a whole bunch of what's called battery eliminators. The reason I'm reinventing the wheel and I'm going this route is those are mostly buck converters. So they'll take a higher voltage and they'll step it down. But the way they do that is they have a square wave drive, and they're very harmonically rich. And the cheaper you get, typically the worse they get for noise. Being that these are going into VTVM, sensitive circuitry, I'd like to keep it a linear power supply if possible, so that was also one of the design requirements. But my design requirements were linear linear circuit, about 1.5 volts output, fixed. Don't need it adjustable, because the battery range, a fresh battery can be anywhere from like 1.7 to 0.8. 0.8's really when they're kind of dead. So 1.5, it's at the top end of a fresh battery, so at least to the meter circuit, this should always look like a very fresh battery, and it should never drift again, and that's why the ohms range has so much adjustment, because as that battery tapers off, you got to be able to zero the ohms range for what might be 1.2, 1, on and so forth. So we're going to have a power transformer. We're also going to have a center tap. And that will go to a rectifying diode. Now I'm hoping, since this is a 2.5 volt transformer, I want to take some stress off of my passive element. So I'm hoping I can get enough voltage off of one side of the coil. So I'm planning on, at least in the beginning, I'm planning on using the center tap in one side of the coil, and this other side of the coil just sit idle. But then we'll go into a bulk storage capacitor, come out of there. We'll go into another capacitor. The particular part that I found, which I'll bring in here in a little bit, the data sheet says it wants a 1 microfarad ceramic cap on the input and the output of the regulator, just to keep the regulator stable. So we will then have our regulator circuit, because it's in a monolithic package, so we don't need to design anything. This is ground. We have some more ground. And then we have capacitor to ground, and then this will go to battery hookup in the meter. So, at least conceptually, this is what I'm thinking about. I've got some proto board. I've got a diode, got a transformer, and as soon as the lab gives them up, which I believe, yes, we have some linear voltage regulators. This is the part number. For those that, I will leave a link to the data sheet in the description below. But these will also give us about 300 milliamps out. 300 milliamps on this transformer, shouldn't stress that at all, given that this is a 1 amp transformer. This is also not the cheapest way to do this. This part's not bad. Diode, obviously, it's dirt cheap. This is a $20 transformer, so this is not the most inexpensive way to do this, but from a noise perspective, I like it a lot better than the buck converters. But to each their own. So, we have very tiny parts. Again, one of the design considerations is I would like this to fit in about the size of a D battery. We're getting kind of close on this transformer. This is pretty up there. But here's 10 of these voltage regulators. These things are tiny. So I may need to make a interface board just to get these to go and do some testing. But if we have to, we have to, and that's what we're going to end up doing. So let me go see what the lab has for parts. Rough math, we'll call this, we'll do a 220 here. Bulk storage, just for charge sake. I may put a high value resistor here just to bleed off the charge of the capacitors. High value being something like maybe 10 mega ohm or something like that. I'm not 100% sure yet. We'll see what we feel like doing, and also what the testing shows up. I would also like this to, I'd like to at least, in theory, if we have a success or a failure, I'd like this to be able to go down to at minimum 110 volts. 100 volts would be more preferable. Okay, wow, it has been a wild amount of time since I had the camera on last, and we've had some wild rides here in the lab. There will be a video on that probably shortly, but because I found out some cool stuff that I do want to share with you guys, but it's more on the facilities side of things. But in the meantime, I had some decisions to make to move forward with this project. One of them being, do I get a store-bought board, or do I whip up some boards here at home or here at the lab? Well, let me show you something that kind of made the decision easier versus harder. Here's the board in question that we've whipped up to do some testing on this battery replacement circuit. And if you take a look at U1, these pads are very small. This is a 1206 part, so this is even surface mount. This is a small capacitor. So there's our cap, and that's a, what is this? This is a 100 microfarad by 10 volt capacitor, and yet we still have pads that are even tinier. So I knew the 1206 parts would be small. Our output's over here, but this IC, I was going to breadboard this and do a couple of other things, but when I saw how close the IC pads were, I had some concerns about doing the etching at home or doing the etching here in the lab and things like that. But the other problem is these regulators are so small that I have a thermal concern with these. These are tiny. So I wanted ground plane or copper pour and a couple of other things. I even brought the copper pour inside these pads to try to give us some heat sinking to the board to dissipate some heat off these voltage regulators, because they are going to dissipate some heat. One of the things that I'm also trying to balance with this design, dealing with these regulators, we're not dealing with a ton of current, just 300 milliamps or less. But for these particular regulators, I'm trying to keep the input voltage low. So I'm trying to really balance a couple of things, because the lower I keep the input voltage, as long as it stays in regulation, the easier it will be on the voltage regulator, because it doesn't have to drop as much current, or it doesn't have to drop as much voltage. That's some of the design decisions that are going into this. So I've got our transformer right here, just to give you an idea how small this is. Here's the board versus the transformer. So it's really tiny. Physical size is important for this particular design, because I want this board, this is a prototype board, this is not finished yet, I want this board to fit in the space that a D-cell battery would, or even a C-cell battery if I can get it small enough. So once we do our load testing and a couple of other things, we're going to dial up the voltage up and down on the variac for the transformer just to make sure it doesn't fall out of regulation. And we're going to test a few things. If all the testing goes good, there's going to be a Rev 2 of the board where it's going to really shrink up. I'm going to actually have to build a footprint for the transformer, because there isn't one. And then I want to compact it, make it as small as possible, and still be hand assemblable. So we have some challenges ahead. I was digging around the lab, and I found out we did not have appropriate sized capacitors. However, these will work. We have a wheel of, what are these? 10 microfarad caps. These are ceramic, so they're going to be, they're 50 volt, and they're X7R dielectric, so these will be fine. This is a power applications, so we're dealing with DC and nothing high frequency. To make this easier to assemble, we are going to do the small parts first. The boards were done at PCBWay. They did not sponsor this video. That I paid full price for these boards. To get 5 of these boards made, it was $25. So do with that information what you will. I do have some fab houses in the U.S. that I use where I'm located, but PCBWay is a little bit quicker with those. This board was turned around in a couple of days, whereas some of the other fabs would have been a couple of weeks. If I have time to order, I don't mind waiting, but I did want to get this going for this video. Output pins are 0.1 inch headers. Come on, focus, camera. Our 0.1 inch headers. So we are good to go there. We'll move those down, obviously. Get us some more pins. More pin. Oh, I'm going to do that with pliers because I'm going to stab myself otherwise. And for those playing around at home, this board is FR4. Nothing special about it. Normal process. And it's about yay thick. All right, we have a board soldered up, and everything's all set. I've got the load connected to the output. We've got input monitoring of the voltage at the back of the diode. We are running single diode rectification. It is regulating. I do have 1.497 volts coming out of the load. And I have the monitoring I have set up is I have the DMM watching the voltage coming out of the transformer. The variac is currently set to 122-ish volts, which is about what the lab's running at right now. We have the other side of the DMM 6500, and then we have the load on the output. So, according to our load, we are in regulation. Everything is good to go. I'm asking for 3 milliamps of current coming out of the unit. Just going to load it lightly, see what happens. I don't know if the voltage is going to fall out of regulation when we load the power supply enough. So we may have to full bridge rectify this, see how it goes, and figure some things out from there. But at 3 milliamps of load, we're still regulating. We're at 142 input to the regulator, and we're at 141. So that's fine. Let's ask for a little bit more. Let's do 0.005. Nope, we're already out of regulation. So falling a little bit too much, even at 5 milliamps. So I need to, next step is to put a full bridge rectifier in there and boost the voltage going into the front side of the voltage regulator, and then watch it for overheat. Okay, we have 3.3 volts coming out of the transformer, going into an unloaded meter. I do think I want to keep that diode in there to get the 0.6 diode drop, because that's going to put it at about 2.9, something like that. So let me hook up, it's negative 3 volts because I have the meter leads on backwards. So let me hook up the full bridge rectifier into the circuit board, and then we'll do some more testing. Okay, I do want to watch the voltage at the back side of the diode, so we'll kick this on again. Actually, let's turn the load off. Kick this on. We're at 2.99. Very nice. Oh, and it goes without saying, yes, I have 3 volts on the back side of the diode. I am dealing with mains voltages on this. On the utility side of the power company, this transformer is hooked into the 120 and back up to the power grid. So, yeah, even though this number's small, we got some angried up pixies running through here, as Abe would say. So we're at 147. Let's ask for the same 5 milliamps. I'll move you guys up to the load. And I will watch the meter. 223 at 5 milliamps. Let's go to 25 milliamps. Nope, that's 250 milliamps. 0.025. Enter. And we're staying in regulation even with a 25 milliamp draw. So now the question is 25 milliamps going to be enough to power an ohms range of a DMM? If I back the variac down to 110 volts, so I'm barely tickling the transformer, I'm seeing 0.9, so it's running like a very dead battery over at the regulator. So I could buoy this up by removing that diode to get rid of that diode drop. Let's try that real quick, see if the circuit performs a little bit better. Okay, we've moved the output of the full bridge rectifier past the diode. So now we don't have the 0.7 volt diode drop, but we do have full bridge rectifier into circuit. So let's see what this does for our loading. We'll turn this back on. It gives me a nice 3 volts at 110 volts into the transformer. Oh, and I can pull 24 milliamps all day long at 110 volts. Bear in mind, this is at 110 volt line voltage, so very, very low today in this day and age. Let's ask it for 50 millivolts. No. Uh, 0.050. There we go. So even at a 50 millivolt draw, which is pretty high for an ohms range, we're at 1.5. We're at 1.05. So a weak battery, but a good battery. Let me hook up do I have ohms on? Yes, I do have ohms on my 410B. I do. Let me hook up my 410B and just see how much current it's putting out and see if 50 millivolts feels like it should be plenty, because I can wind this up to, so like 117 volts, and I'm back up at 1.2 volts out of the battery. So that's plenty of power. How's my regulator doing? Are we getting hot? No, we're not even getting warm. Okay, the post office has come, and we have gotten some parts. So I've taken out the small 2-volt transformer. We've gone to a slightly larger 5-volt transformer, but we're also on a 2-amp transformer now as opposed to a 1-amp, so should have some less transformer loading and things like that. So let's fire up the variac. I have, again, the DMM watching past the diode, and we have the load. I'm a little more concerned because we bumped the voltage. I have to watch that we don't put more than 3.6 volts into the regulator. That's all it can take. Since the board already needs a Rev 2 and this transformer is way bigger, what I'm thinking at the moment is possibly putting a Zener diode in to protect it. I'll be able to vary the line voltage with the variac a bit, and that'll give me a are we in good shape or are we in not good shape determination. So let's fire up the variac, and if the magic smoke comes out, you guys will be the first to know. Because I'm not looking at that, I'm looking at something else. Actually, I'm looking at the DMM. Already looking better. So I'm at 55 volts on the variac. I've got 2.8 volts into the front end of the IC, measured at the diode. And I have, we are regulating. And what I thought, we are way too high. So unloaded with this particular transformer, with the larger transformer, we're at 63 volts and we're at 3.2 volts at the diode. So let's turn on let's ask for some current. Yeah, 50 milliamps and it crashes out. So with a 50 milliamp draw, the transformer's loading down substantially, actually. This is probably getting... No, that's not too bad yet. So I got to 89 volts, and I'm at 3.6 into the front end of the IC. Nice solid regulation. If I set this to 100 milliamps, we fall again to 3.2. So I'm up to 100 volts at 100 milliamps of current draw. So we are definitely going to have to do something with the loading on this one. Let me try the transformer single-ended, and we'll see what happens. We'll get rid of this. We'll get rid of this bridge rectifier. Do it pulsed through there, and then we'll check that. We'll check the voltage. But I had a feeling this transformer was going to be a bit big and was going to overvolt this. Try one more test where I have now the protection diode in circuit. I didn't have that there that way before. So let's see if that additional 0.6 volt drop will do me good. We're going to put a draw on for about 30 milliamps. Well, that is actually looking a lot better. We're at 95 volts. I have, let me get a pointing tool here. What do we have that's insulated? Here we go. So I have 3.6 volts on this side of the diode, and we have, what do we have over here? We have 3.9 over there, so we got about a 0.3 volt drop through the diode, which is fine. We're pulling about 30 milliamps. Yeah, that regulator is still fine at 100 volts. All right, let me increase the load to 100 milliamps. Ow, whoa, at 300 milliamps, it's getting a little toasty. Okay, we've changed the config up a little bit. We're on half-wave rectification, or we're on single diode rectification, center tap, and 100 milliamp load, and we're going to check the output voltage and see what happens. Let's pop this up to 110. Yeah, that's not going to work. So we do need the full wave rectification. I get about 0.6 on the front side of the diode, and 0.4 at the output with 120 volts input to the transformer. So, okay, I'm going to set this back up for, I'm going to look at the data sheet first of all for this part, because something's a little strange, but I need to see what Vmax is. I need to triple check that. If Vmax is high enough, we'll just let this run and let the regulator do its thing. But definitely going to need the, so for the Rev 2 board, we're going to need the full wave rectifier along with possibly some Zener limits in the front end to protect the circuit and go from there. Okay, something wasn't making sense when I was doing some testing. So I decided to break out the Keithley 2281 and feed this circuit from the rectified side of the diode. And I've given the Keithley 300 milliamps at 3.6 volts, and the load is set up for 300 milliamps, and the Keithley's not on. So if I fire up the Keithley, we have a 3.6 volts, and then we also have right around 300 milliamps. We have good rectification and right around 300 milliamps. So the rectifier is working correctly. So why, when I have it hooked up to the transformer, may it not be working correctly. Well, next step was to bring these back down to the DMM. We shall move you guys down to the 6500. We're going to fire this up right around 120 volts. 120 volts. We got 1.6, but the circuit's still struggling. I got 2.5 volts on the output. Well, I had a suspicion, and I have 700 millivolts of ripple on this line, so I do not have enough filtering, which means, for sure, that capacitor is too small, at least for this load. Now, what happens? Watch this. We have our 700 millivolts of ripple while I have the load turned on, and we have 2.5 volts coming out of the regulator. If I switch the load off, my ripple falls to almost nothing. So what I'm going to do is, hopefully I can still use that smaller transformer. I'm going to hook the smaller transformer back up, and I'm going to increase the size of that filtering capacitor, because obviously that's, I think, a 10 microfarads, way too small. So I'm going to increase the size of that filter capacitor, see what happens. Okay, we're back to small transformer, full bridge rectifier. And we've added a 1000 microfarad 6.3 volt capacitor. Small transformer, full bridge rectifier, and in we go. All right, with the variac turned on and set to 120 volts, no load at the moment. We're at 3.3 volts, nice and healthy. I like that. And we don't have the protection diode in, so that is also good. We're going to turn some load on. Okay, we dropped from 1.4 volts to 1.9. We're down to 1.8. And we picked up 436 millivolts of ripple. So even that 1000 mic cap is too small. We're going to go bigger. Okay, we'll chalk this up to comically large capacitor. This is a 1500 mic by 63 volt. This is the 1000 mic by 6.3 volts. So obviously, if I'm going to build a bunch of these, this is a total waste of money. I'll order some 6.3 volt caps and they'll be fine. We'll set the load to 100 milliamps, or 300 milliamps to check it. And I'll move you guys over to the 6500 so you can see what's going on. 6500, we are at 300 milliamps. Turn on 120 volts. All right, we're at 1.9. This should give us regulation. It does. Okay. What's our ripple? 300 millivolts of ripple. So what I may end up doing is bumping it up to a 2200 microfarad capacitor. Maybe even slightly bigger, but I need it at 6.3 volts. So I need a bunch of capacitance, but not at a high voltage, which means the cap will be physically small. Let's check and see what happens. I'll move you guys up to the load. We are up at the load. So let's move this. Let's dial this down to 110. So I still get a volt at a 110. So again, we're having probably some ripple problems. No, I'm having a little bit of voltage fall. So we're still quasi-regulating. 1 volt is still okay for a battery. It would be considered a good battery. 0.8 is about the lowest you want to go. We'll bump this to 117. That's 117. 117, we have good voltage. It's about the lowest I see around here these days. And if we bring it up to 125, yeah, we're still fine. And our regulator isn't even getting warm. So I'm going to leave this set at a pretty toasty voltage, 125. That actually gives me, we're well under. It's 2 volts into the front end of the IC, so I don't even need the protection diode. What have we learned for Generation 2? Because there will be a Gen 2 of this board and circuit. This small power transformer is plenty, which is good, because I didn't want to get the transformer, given that my size requirements are about the size of a D-cell battery. I didn't want to get the transformer much bigger than that. Shut off the solder sucker. We are going to need full bridge rectification, so that's fine. We will not need the protection diode that's hanging out down there because I have the rectifier dialed in. I'll need to see what I can find for about an amp-ish full bridge rectifier. The bulk filtering capacitor right after the protection diode was woefully under-spec'd at 100 microfarad, so I need to be up 2200, 3500, 3000, maybe 5000 microfarad to smooth out the ripple on this circuit. That's what was causing us problems with the voltage regulator, and those two decoupling caps next to the voltage regulator are making it run pretty good. Circuit's not even struggling. Let's move you guys back to the DMM. This 2 volts DC is actually at full load, 300 milliamp, and this AC ripple is also at full load. I did check my HP410B, what it supplies for current for the ohms range, because this is what this is designed to go into. And it was 100 milliamps at 1 ohm scale, and the current went down in decades as it ratcheted up in decades. So at 100 milliamp, our ripple goes down to 100 millivolts a ripple, and we're at 2.5 volts for regulations. So bumping up that cap is definitely going to help it, but I'm also not at the 3.6 volt limit either. So very healthy, and we have a high line side. I'm at 125 volts on the line. Let's do 10 milliamp just to make sure it's not going to go nuts. We go up to 3 volts, still have 600 millivolts of swing there, so everything looks good there, and my ripple is down to 10 millivolts of ripple. So at that loading, that capacitor is fine. The capacitor is going to be totally okay if I bump it up. So lots of capacitance is needed, but otherwise the design is nice and sound, and I'm really stoked that transformer is going to work. Thanks for swinging by the lab, taking a look at this phase 1 of design for this linear power supply for battery replacement in VTVMs. I will release this schematic if anybody wants to see V1 on Patreon. For all the patrons that are there, thank you for assisting in the lab. You guys do help to keep the lights on. And we'll go from there. I will also be releasing updates to this PCB and a few other things as things progress. But for this particular project, if anybody wants to play with this, I will release the CAD files also. So I'll put I'm using KiCad for PCB design, so if you grab KiCad, which is free from the internet, you'll be able to take a look at the files and see what I've done. One thing to note about this is this does play with mains voltage. On this side of this transformer, you have 125 volts, at least in my world, of angried up pixies, as Ave would say. So extreme caution is needed. I do hit the safety button a few times, and I do hit the safety button pretty hard. I've worked on stuff that could kill me with zero trouble, and I'm talking about if anything goes wrong, I will cease to be, as in here 1 minute, gone the next. always something to be aware of. On this side of the transformer, I have 100. I have 3.6 volts, 2.5 volts, 3.6 volts. But still, I still respect it, even though it's a couple of volts. So definitely something to watch out for and keep an eye out. With that, I'll close out this video. As always, I will see everyone in the comments section, and I look forward to reading all the comments and am there between videos. As always, more is on the way, and I will see everyone in the next video. I've got some computer work to do.